Okay.
All right. So this presentation is an analysis of the simulation result we obtained in the last week. So in the last meeting, so analyzing the differences between the simulation and the theoretical results mentioned in the paper. So the parameters and range used for this analysis are as follows. So the capacitor is 12 nanometer, and and this is how the parameters actually work. Actually, the IPCC will be 40.7 instead of 40, so instead of 4. Sorry for this mistake. So for full bridge rectifier SBR, this is the graph. This is the graph we get. So it's the output voltage versus output power graph, and the point that is actually mentioned here is the peak. So here for the highest power. And as you can see, this is the theoretical result obtained in the paper. So in the simulated result, if we look at here, so the maximum power is 8.42 microwatt, and the power we obtained at 898 millivolts. As we can see in the theoretical result for full bridge rectifier, the maximum power is about 8. Is about 8, and it is at about the 0.8 or 0.9. So basically, the results from the paper simulation are actually the same for full bridge rectifier. In switch only rectifier, so for switch and the rectifier, this is the graph we obtained. So this is the graph we obtained for the switch only rectifier. And this is the graph, this is the theoretical graph for the switch only rectifier. As you can see here, the peak is at 1.7 volts and the peak is 18.57 microwatts. While for the theoretical result, the peak is at 2 volts and the peak is like 22 microwatts. So there is a difference here, and the difference is about 15.59%, which is greater than 10%. So that's a matter of concern. Now, analysis of the error. So firstly, we take V out equals to 1.2 volts. So for 1.2 volts, there's the equation for power where V rect is going to be equal to V out, which is 1.2 volts. So we can plug in, and the theoretical power comes out to be 18.4 microwatts. But as you can see in the simulation, the result was 16.85 microwatts. So if there is an 8.47% error in the result. And the graph in the paper and the theoretical result we obtained from this formula are actually kind of same. But as you can see, our simulation actually gives a different result with the error. So here's the current we get for the out equals to 1.2 volts. A power equation will look like this. And actually using cadence, use a calculator tool of cadence to get that our I out average, the average current is this the 14.04 ampere. So if we plug in, we get the power of 16.84 microwatts. So what it should be, so that's the same as we saw in this graph over here. So that means the I out, the output current is where the problem actually lies. So the problem is actually lying. Let's see for another voltage. V out is equal to 1.7 volt. Remember that at 1.7 volt, if we go back to the graph, so at 1.7 volt, the switch only rectifier power graph was at this peak. So that's why we can actually analyze at 1.7 volts, and at that voltage the theoretical power is 21.5 microwatts, but the simulated power is only 18.57 microwatts. So the error is there is still a 13.54% error in the result. And notice that the error is actually increased, and we're going to talk about it more later. Now, if we calculate the power over here using the calculator tool of cadence, we actually see that the I out the average output current looks like this. And if we plug in, we get a power of 18.5 microwatt, similar to what we obtain in the graph. Therefore, we can actually once again conclude that the I output current is where the problem is actually is. And then we can actually test at another point, which is the output, which is where the theoretical peak should be, which is at 2 volts. If you remember from this graph, as you can see here, the theoretical peak point should be at 2 volts. So if we plug in now, if we plug in 2 volts here in this equation, we get 22 microwatts as the maximum power. But the simulated graph gives us only a power of 18.16 microwatts. So that gives an error of 17.41%. That's even more. And if we actually now try to calculate the power, we once again see that the output current is where the problem is, because the output current looks like this. And if we calculate the power, we actually get the result exactly same as the simulated one. So the output current is the problem here. So the observation is this: the output current is the reason for the discrepancy between the simulated and theoretical results. And actually, there is an interesting trend, and the trend is that if we do a graph of the error versus the V out, the output voltage, we actually see the graph actually looks like this. So it's actually kind of a exponential kind of looking exponent that looks like an exponential graph, as we can see right here, and the non-linearly increasing. This is basically the output is error. So as we saw before, that for 1.2 the error was only 8%, but for 2 volts the error was almost 17%. So the error is actually increases with this increased V out. Here, this is the formula I use for the error calculation. Thank you. Okay.
Okay. Let me share my screen.
Okay.
First, you should, as I mentioned before, you should change this graph into background white color.
Okay. How to do that?
Look back the last video. I already.
Okay.
How do you make this graph? You use
Excel.
Excel.
No, I use Microsoft Excel.
So error increase with V out.
Yeah.
So let's check. In here, the input IPJT is the same, right?
Yeah, the 40.7.
IPIC same. So when you increase the voltage, here is I out and IPT. So increase the voltage. You can see the difference between IPIT and I out, right?
Yeah.
This I out is smaller. Now you find the issue come from I out, but how to make the error, how to reduce the error.
Actually, like, why is I out is doing the error that I don't know. So.
Because anyway, this guy also do simulation. The author also do simulation like us, right? But he can make, he get the result and theory same. But we still have error. So we should find how to solve the error, right? He simulated and the result is the same. So
exactly, what should we do? So basically, why the output current is not correct, not accurate.
So actually, in here, full rate rectifier, no problem, right? Simulated result and theory the same. So in here, we added the switch, right?
Yes.
From the rectifier. So issue should come from this switch, right? Because this is not a problem.
This part is saying is different.
Right?
Okay.
In this circuit, it works well, right? In here, we just add a switch and it's make problem. So problem might come from this switch, isn't it? This circuit only have a rectifier and a switch. So this rectifier is no problem. Maybe first you should check whether the rectifier and the rectifier is the same. So let's check. Maybe we make a mistake. So here 12 micro, 2 micro, 500. Ten fingers. Same sign. Oh, some different here, right? Do you see the difference? Here 5, here 2, right?
Oh,
Different in size.
But it's I mean, we should compare FBR with the switch only, right?
Yeah. But in this circuit, we do make mistake, right?
Hmm?
We make this most should be the same size,
Okay.
but we, although we make mistake here, but this mistake is not a big problem, so the result the not affect, right?
Mhm.
But we should make it similar for on this dial
Hmm.
here 5 2 2 2, yeah, so it's the same here and here same, so it should come from here and here -1. Let me check if I change this switch side. I'm like 20. Now here is 18 or 8. We will increase the power. This is a little increase. The power increase little, right? Isn't it?
Yes, yes, yes.
Maybe 2 volt. 2 volt. Here is increased,
Yes,
right?
yes. So the power is actually increased, yes.
So you should change power switch and you might change the voltage supply here.
Mm.
And you change
Voltage supply, what voltage supply? Can you repeat the part of the voltage supply?
do you see that?
Mhm.
You might change your wait. We when the current become zero, right?
Mhm.
When the current become zero, we open switch
Yes.
to flip the voltage on PJT, right? To
Mhm.
flip it fast. Here I'm making 10 microsecond. The
Mhm.
time I close the switch, but
Mhm.
you can change here. Let's say um, the switch. Now I make 10 microsecond. It is 18.3, but let's say 5 seconds, 5 microsecond.
Mhm.
Almost the same. Let's say so it look like the time I turn on the switch not affect the output power,
It shouldn't be.
but it's mostly come from switch side maybe. So your homework you should anyway you should is your work. You should improve the switch only by changing the switch
The switch part.
parameter. Switch by turn on the gate content. Okay, anyway, you should improve this power like that. You got it right? It is all good. Try your best to make the highest as short as possible. You might change the time you turn on switch. Here, I turn on the switch at -1 microampere, but you might shift this graph, right? You might turn on in here, exactly 0. You can change it by change the delay here. The delay your pulse. You got it, right? You might ask, for example, more 100 nanosecond, and then yes, the pulse will delay 100 AB 100 nanosecond. You got it?
Okay.
You should optimize the time you turn on switch and
the width of the switch.
yeah, on your parameter, you should optimize this switch to improve your power. Got it? Okay. Do you have any question?
No, actually.
Okay, so Thái, please share your screen.
Yeah. Can you hear me clearly? Yeah. Can you hear me?
Yes.
Yeah. Okay, I should share my screen. Can you see my screen?
Let me stop sharing.
Okay.
Okay.
Okay, now you can see my screen.
Yeah.
Yeah. In last 2 weeks, I studied about research about the chapter 2 that you sent me. It is basic, most derived physics, as well bias flip thesis. So as Ryan said before, so I will present overview of that I learned. The first one is the most device physics. I learned about the structure of more device. It have two gate, the gate and the sort and drain, and the inversion take place when we put thresh voltage in the gate. We can create formation of depletion region. Also, when the voltage of the gauge is reach the threshold voltage, it's a inversion layer is the take place. And also the current will flow from the gate, source to the gate to the drain.
Can
It
one,
is
wait. Can you
sorry.
open the slide bigger?
Okay.
Yeah. Right.
Yeah.
Okay.
Because in this slide is we have p substrate, so almost of it p dot, so almost of them is a house. So when we put the positive voltage in the gate, it will push the positive voltage in the house like this, and it can have more negative ion in this channel. So if we push increase the voltage in the gas, it will have more negative ions. And when it reach the threshold voltage, we can create the region from the channel from the gate to the from the short to rain. Oh, sorry. It is the formation of the free threshold, and also next to the most current voltage characteristic is the formation came from the I read in this book. It's the design analog this book. It initially is made from the column per meter. Is the current is equal column per meter multiplied with the bond is the vector. Vector is also we have uh, from formulation of the Q is the equal W multiplied with C and voltage. It can be understand that is the Q of capacitor is the C multiplied with the voltage. Also, in the after I take a calculator, I can have the IT in this line. And when we draw the current voltage characteristic, we can have the diagram like this. It can be such as the same as the parabol, and we can have the IT max when the VTS equal VGS subtract with the V thread voltage. And when we have if the VTS either very low as compared to the two VGS subtract with the V direction, is the it can operate as a resistor. So it's a liner. It's the overview of the MOSFET thesis. I also understand the nature of the some equation, but it's so long to explain. So I just talk overview. In next slide, I will present bioelectric modeling. As we can see in this slide, the bioelectric harvester can represent as the current of IP and capacitor CP and resistor VP. Inductor can represent as the mechanical mass. Capacitor is the mechanical stiffness, and the resistor is the mechanical loss. And if we have harvester as well the loss, if we have the independent match to combine of them, we can guess the power mass in thesis that in this equation. So initially we have full bridge rectifier. If in the positive half circle, initially the current source can charge the CP when CP either get to either higher or equal than Vref plus VD. The diode can be turned on, so the current can flow into the capacitor Crect to charge this, as we can see right here. When the current source either change the direction, we can discharge the CP. So we can calculate the power loss in this equation, because we have to multiply with the capacitor CP and Vref like this equation, because in both positive and negative half circle, we need to charge and discharge CP. So it's like a lot of energy loss. So after take a calculation, we have a period for this equation. We can get the period mark when the Vref is equal VP multiplied with 2. And because of loss a lot of energy, so we take into account the voltage double. In this voltage double, we just use two diode to adjust to take into account. In the positive half circle, we charge the CP when the CP is equal or higher than the Vref plus the V diodes. So the IP is flow into the Vref. But in negative half circle, it don't flow into the Vref. It spend a lot of time in the negative half circle to discharge the CP. So in this slide, you can see that instead of spend time in negative half circle to discharge the two circle to try and discharge the capacitor in the voltage double, we just use one positive half circle to charge and negative half circle to discharge. So it's a gas loss energy. Is the energy loss can calculate in this equation. The first part is the 2 CP VP, and the second is the CP Vref. Maybe we use the voltage double is the take a loss energy as compared to full bridge rectifier, but it's also loss energy. So we use switch only rectifier to make more effectively. Instead of using the diodes to discharge the CP to the ground, we just using a switch M1 to discharge it. So when in a positive on positive and negative half circle, we turn on the switch M1 to charge the CP and then discharge the CP. So it's just take a lot of energy. So we can have energy Q loss and this equation 2 CP plus multiplied with Vref. And finally is the bias Phillips rectifier. We have more inductor as compared to past rectifier. Because we use inductor, so it can flip the voltage. Because when we discharge the CP, we take many times. So if we have inductor, can provide more current to the CP, so it can charge fast. So it's loss energy. It's the overview of my research. I also read some paper about the triboelectric. I just read overview about triboelectric and this. Okay. But it's not much insight in the in the triboelectric, we don't have the same function as compared to the piezoelectric. In the triboelectric, we have a higher and the lower voltage rectified output. And but maybe in the test I don't have much problem, but in the simulation in the Cadence in the past I simulate is okay, but it run, but it cannot create the result as I hope. But now I cannot run it. I have this. I use the simulation from Brohom, and I run simulation using the ITE and like this. But it have in the last week I run is run okay, but now it have errors like this. It unsuccessful. I don't know why is that. I can paste this in Vision. Can you see that?
Yes. Fail to generate Nestle.
Meeting and
Clean the run directory and Nestle. Did you turn? Did you give me your TeamViewer ID?
Okay.